Welcome back. Let us take a new topic in electric power system. We will discuss the economic operation of power systems. So the introduction goes like this. The basic goal of this economic operation of power system is to minimize the production cost. So we need to minimize the total cost which is involved with the production of power, maintaining the voltage magnitude at each bus to be stable. Load conditions vary with time, whether we are talking about day and night or different seasons, whether it is winter, summer, and so on. So constant power generation is unrealistic. We cannot get constant power generation, and power generation will follow certain load pattern which will change with respect to the seasons or different time. To optimize this power, we say that to be a load dispatch problem, we focus on two important aspects. The first one is the economic operation that must adapt to the load conditions. So when there is a change in the load, then the economic operations should change, maintaining the stability of the voltage magnitude so that the production cost can come down. Second is basically the turbine governor control, which must ensure the optimal generation is possible. Economic operation of power system. Power was initially supplied by the most efficient plant at the light load condition. So if the load is less or light, then the power basically was supplied by the most efficient plant, because you may have different plants, whether it is hydroelectric power plant, nuclear power plant, that is producing the power. When the load increased, the most efficient plant supplied until its maximum efficiency was reached. So this load is not constant, it will keep on varying, and if this load is increased, then the first point what we have seen, that the most efficient plant, it will be supplying the power to its maximum rated capacity. The next most efficient plant then supplied power until its maximum efficiency. So we have so many plants working in parallel with each other. So once the first plant has supplied the power, the next plant will supply the power up to its maximum efficiency. These continued from the most to the least efficient plant to meet the peak demand. So from the most efficient plant to the least efficient plant, we will be moving to meet the peak demand. However, having said this method, it failed because to minimize the total cost of generation. So when we talk about the cost of the generation is not minimized with the method which we follow here, going from the most efficient plant to the least efficient plant. So an alternative method is needed to account for the total generation cost of all the power units that are supplying the power. So we should talk about the economic distribution of the power between the loads when there are different units of plant. So there is a variable operating cost of each unit which are expressed in terms of power output. The fixed operating cost is to set up the plant, and the variable operating cost, which is the running cost of each unit, are basically expressed in terms of what is the power output we are providing. The fuel cost is the dominant cost in thermal or nuclear unit. Fuel cost must be expressed as a function of power output. So power output and fuel cost must be related with a function. Other costs like the operation cost or the maintenance cost can also be expressed in terms of power output. Fixed cost, which are basically the capital cost and depreciation, are not included in the fuel cost, because the fuel cost are the variable or the running cost. Fuel requirement is given in rupees per hour. So we are taking the time duration of the power to be produced and the unit which we are taking in terms of rupees in India. So rupees per hour. Now suppose for unit I, any particular unit of power system plant we are taking, then the cost which is involved in rupees per hour is expressed by the expression in rupees per hour, which we have a non-linear expression in power. So we have a constant A by 2 pi square plus bi pi plus ci. So these are basically the constants, and we have a second order quadratic equations. The operating cost is approximated by a quadratic function of power unit is in megawatt versus the cost which is in rupees. So the power which is output generally it is very high in the range of megawatt, and the cost which is involved in rupees, and these form quadratic function. The incremental operating cost lambda is basically calculated as the differential of these operating cost with respect to the power. So we are having AIPI plus BI. Again, the unit is in rupees per power. Power unit is in megawatt hour. For two units with different incremental cost, load transfer from higher to lower incremental cost reduce the total cost. So we have to minimize the total cost. So what we need to do, if for an example, if you have two units, then in that case, the differential incremental cost, this incremental cost function lambda I has to be transferred from the higher to the lower incremental cost plant. These continues until the incremental cost are equal for both the unit, which is called optimal point of operation. It means the lambda 1 of one unit should be equal to lambda 2 of the second unit, then we can have the optimal point of operation. This principle can be extended to n units in a plant, and we can have the total fuel cost as the sum of the individual fuel cost of the plant. So summation k equal to 1 to n, where n is the total number of power plants and Fk is the cost of a particular plant. So the total power Pt is the sum of the powers supplied by each unit. So this is again summation k equal to 1 to Pk. So this is in terms of cost and this is in terms of power. The objective is to minimize the total cost involved with respect to power. So we will be finding the differentiation of the total cost with respect to power, taking the differentiation of each plant with respect to P1, P2, Pn and so on. Since the total power is constant, so the differentiation of the total power will be equal to 0 because for a constant differentiation is 0. If we multiply by the incremental cost lambda and subtracting it, the expression, we get it in this form. And this form equality holds of the expression, the differentiation of the fuel cost with respect to the power of a particular unit minus lambda, the incremental cost, is equal to 0. And this is valid for all the power plants from I equal to 1 to n. This leads to a function lambda, which is the incremental cost, and this is equal for all the corresponding power plants, which is generating P1, P2 and Pn, and their corresponding cost function is F1, F2 to Fn. This equation is known as the coordination equation. If we try to graphically see this equation, so on the y-axis we have the fuel cost with respect to power for two particular power plant. Then for a constant lambda, which is the optimal lambda, we can find out like this curve is intersecting at what optimal value of the power. Similarly, this cost is intersecting at what optimal value of power for the other plant. So P1 and P2 conjugate demonstrate the optimal power production by the plant 1 and 2. And this is the optimal incremental cost which is coming from the coordination equation. Let us see the generating limits. Not all units are always available to share the load due to scheduled maintenance. So there will be maintenance in the power plant. It means all the units of the power plant will not be functional. It is not necessary to switch off less efficient unit during off-peak hours. So advice is not to switch off the less efficient unit. You need to keep that also. Shutting down and starting up the unit incur cost and may take about 8 hours to restore and synchronize. So if the less efficient unit we are shutting down, then it will take around 8 hours to restore the power, which will incur the cost. To handle such power demand changes, extra unit may be required, creating a spinning reserve. So if you have the extra units which are present in the power system, so that will create some spinning reserve. The optimal load dispatch must include startup and shutdown cost while ensure the system security. So in order to find what is the optimal economic operation or optimal load dispatch problem, we also need to include the startup of the power plant as well as the shutdown of the cost to maintain the system security. Power generation limit of a particular plant, ith plant, is greater than the minimum value of that plant and less than the maximum of that plant for I equal to 1 to n. So n is the total number of power plants. So maximum power capacity of each unit is defined, which we need to obey. The minimum ensures thermal stability. So this minimum value of the power for the particular plant, it will ensures the thermal stability of the boiler in thermal or nuclear station. So a particular power plant has to produce the power which will be lying between the minimum and the maximum value. A unit must produce a minimum power to maintain the boiler's design operating temperature. So if the unit is producing at least the minimum power which it has to produce, because it has to maintain the boiler design, and hence that power will not be given to the consumers. So what is the economic sharing of loads between different plants? So what we discussed is basically the economic operation of a single plant, focusing on how the load is shared among its unit. So let us take this discussion further and analyze ignoring the transmission line losses, assuming they were part of the load. So considering that multiple plants are connected by the transmission lines, line losses must be included in the economic dispatch problem. So we should also include what is the transmission loss. So if we include the transmission loss expression, so this is the total power which is produced by the different plants minus the transmission loss is equal to the total power, which is the economic dispatch power. Now this power PT is constant, so again the differentiation will be 0, and if this differentiation of the power loss, we arrange it in terms of the corresponding power of each plant individually, then what do we get is basically again the mathematical expression similar to what we got it initially. So if we sum up all this expression, so I equal to 1 to n, the summation of the differentiation of the power of a particular plant with respect to its fuel cost plus lambda times the power loss by plant power minus lambda multiplied with dpi will be equal to 0. So these equations should satisfy the form of involving the function involving the power, cost, the loss and the lambda. This is for all plant valid. Now again, since the incremental cost has to be equal, so we will be including one new term in the previous expression, which is L1, L2, Ln. What is this Li? Li is the penalty factor. So we are basically including the penalty factor for each plant so that the incremental cost may be equal, because we are including the transmission losses also. So this expression of Li for any plant I equal to 1 to n is given by 1 minus the total differentiation power loss with respect to a particular power plant. Now if you have an area where n number of units are there, the power generated is represented by the total powers P1, P2, Pn. This is represented as transpose. So this is basically a column vector which is given by the transpose expression. So power loss expression is given by this power transpose multiplied with the constant which is known as the loss coefficient constant matrix, which is a m cross n matrix, and this is symmetric also. So that is given in the form of B, where if you observe these values will be equal. So this is a symmetric matrix and only the diagonal values we need to know and the first row we need to know. So Bij, the particular element Bij are the loss coefficient. So power loss expression PT BP will be used to find the total power loss. These coefficients vary with plant loading. So when the plant loading will vary, the coefficients Bij will vary. But for simplicity, they are often assumed constant when calculating the penalty factor Li. So we have to calculate the penalty factor. So this Bij value we need to assume to be constant, which is however not, because they will change with plant loading. So we have studied little bit of theory of economic load dispatch. Let us solve 3 important problems which will clear our idea. problem number 1. So there are 2 units in a power plant with fuel cost expression given by this one. So if you see, this is a quadratic expression. Unit is in rupees per hour because this is what we are talking, the fuel cost involving for power plant 1 and power plant 2. And the expression is quadratic and there are 2 plants involved. So 2 expression of P1 and P2 will be there. First part of the problem asks, determine the economic operation schedule and the corresponding cost of generation for a demand of 180 megawatt. So 180 megawatt is the demand. So it means the total power that we need to produce, P1 plus P2, has to be 180 megawatt. So what is the economic operation schedule that we need to follow? And if the load is equally shared by both the unit, determine the saving that is involved by the loading of the unit optimally. So power saving or the cost saving we need to determine. So the first part, which is economic dispatch problem, and here we note that the fuel cost derivative relative to each unit output power must be equal. So this value, whatever we got it, is equal to lambda, that is the incremental cost of the fuel cost with respect to its corresponding power, the expression. And the expressions are already given in the problem. So if we take the differentiation of the first expression with respect to P1 and the second expression with respect to P2, and we equate this derivative, we form one equation which is involving 2 variables P1 and P2. So we need one more equation which will come from the total power demand expression, P1 plus P2 equal to 180 degree. Now we have 2 equations in 2 variables. We can solve it and find what is the power P1 and P2. The total cost of generation is basically the sum of the individual cost. So we can sum up F1 plus F2. Now these power P1 and P2, we can substitute in the given expressions F1 and F2 and we can get what is the total cost which is involved with the individual plants. Now second part of the problem where we talk about the economic load sharing. So the load is equally shared by the 2 units. So it means the power of 2 plant, which is summation 180 megawatt, has to be distributed between plant 1 and 2, which gives to be 90 megawatt. The total cost of generation remains what we got it from the previous case. So if you subtract the total cost of generation minus what we got it earlier, will have a saving of 0.57 rupees per hour. So these power P1 and P2 we have to substitute in the function F1 and F2. We have to add those to get the total cost of generation. So what is the saving that we have achieved? About 0.57 rupees per hour. Let us take the second problem, which is generating limit problem. So here we have 3 plants and these 3 thermal plants, their expressions of the fuel cost are given. So we have 3 variables now, P1, P2 and P3, which are the powers of each individual plant. And these powers P1 and P2 and P3 have the lower limit, which is 30 megawatt, and the higher limit which is given for P1 is 500 megawatt, P2 is 500 megawatt and P3 is 250 megawatt. What is the optimal schedule for a load of 1000 megawatt? 1000 megawatt maximum demand means the summation of P1 plus P2 plus P3 will be equal to 1000 megawatt. So the solution again start with the optimal dispatch problem where the fuel cost with respect to its individual power differentiation will be equal. So we can have the differentiation of the expressions involving F1, F2 and F3 and we can lead to 2 important equations, and the third expressions that we get is basically the total power balance constraint. So 3 equations in 3 variables can be solved and we can get the values of P1, P2 and P3. Now if we observe, the maximum limit of P3 was 250 megawatt, which is violating the power which we got it to 76.32 megawatt. Other 2 plants it is not violating because the upper limit was 500 megawatt. So 250 megawatt we have to set for P3 because it is violating the maximum limit, and the remaining load, because total is 1000 megawatt, so the remaining load of 750 megawatt which is to be distributed between P1 and P2. So P1, P2 plus P3 will be coming to be 1000 megawatt. Now the expressions that we get, the point For P3 now it become constant, which is 750 watt, and P1 and P2 is not known. So we can solve the other two expression to find out what is P1 and P2, given P3 is the upper limit of the plant which we set it. So this is the generating limit. Problem number 3 for economic load dispatch, where we have two buses which is generating the power P1 and P2, and the load is connected with bus number 2. The fuel cost expression for the two power plants are given, which is again quadratic in nature. If 200 megawatt of power is transmitted from plant number 1 to the load, so from 1 to the load certain power is going, which is 200 megawatt. A transmission loss which is involved in the transmission line is 20 megawatt. Determine the optimal generation schedule and the cost of the receiving power to the load demand of 204.41 megawatt. So this load is demanding this power 204.41 megawatt, and 20 megawatt is going in the transmission losses which is involved with the transmission line. So we know the expression that we have set for power loss, P transpose into constant matrix B into power, will be the total power loss. And since the load at bus number 2, P2 will not have any effect on PL because the load is connected on bus number 2. So we can have B12 and B21 will be 0 and B22 will be 0. So all the expressions which are involving the bus number 2 will be 0, and the power loss expression will be only B11 into P1 square. If we expand this equation, setting these values of B12, B21 and B22 to be 0, we will get this expression. Now 200 megawatt of power P1 and power loss 20 megawatt, we can substitute in this expression to find what is the unknown B11. So B11 we can find out, and after knowing this B11, we can put it in this equation to find what is PL. So the optimal dispatch problem, where you have the penalty factor to be multiplied with the fuel cost derivative expression to find the lambda, PL is a function of P1 alone. So the penalty factor L1, which is the expression given by 1 minus the total differentiation equation of power loss with respect to P1, we will get this expression. The penalty factor for 2 will be 1 because there is no power involved with P2, and hence we can substitute these two equations in this equation, we will get this third equation, and we can simplify this equation to form the expression which is in the form of P1 and P2. Now these two expressions are two functions which are basically the powers involved P1 and P2, those are the variables. So two variables in two equations. We can solve these equations using Newton-Raphson method, where we need to find the Jacobian matrix. The Jacobian matrix is again the differentiation of the fuel cost with respect to P1 and P2 expression. So from the first expression that we have derived, so we can find out what is delta F. So delta F, the change in the fuel cost, is Jacobian and the change in the power. So if we take the initial estimate with the values, so we can substitute that in the expression and take the initial estimate to be 162.94 and P2 to be 41.47. Now this estimate we can put it in the iterative solution to find the Jacobian matrix and what is the update value of delta P1. So delta P we can add with the initial values of the P to get the updated value of PI conjugate. So this is the optimal value. Now these values what we get it after the first iteration. So we can see that it took about 6 iterations to converge and get the values of P1 and P2, and the total fuel incremental cost we can find out from L2 dF2 by dP2, which comes to be 19.99, or approximately this comes to be 20 rupees per megawatt hour. So this complete our discussion on economic load dispatch problem. We will discuss a little bit more on the frequency control and APC problem in the next coming lecture. Thank you for now.